All right, so last time we started talking about Borel-Cantelli lemma, and Borel-Cantelli lemma involved something about the probability of the limb soup of a sequence of events. We said that there were two parts to the Borel-Cantelli lemma. We stated both of them. We proved the first part. We were in the middle of the proof of the second part. That's where we had to stop. So now what I'm going to do is I'm going to go ahead and turn off the camera, and I will go ahead and share the iPad screen. I hope the screen is visible right now. Okay, so here's just a quick reminder. We talk about Borel-Cantelli lemmas. So let omega fp be a probability space. And suppose I have an n going from 1 to infinity, which is a sequence of events. Okay? Then we define the limb soup of an as the intersection n going from 1 to infinity of the union k going from n to infinity of ak. We saw last time that omega is in limb soup of an if and only if omega is in infinitely many ans. In other words, the limb soup is the set of all points in omega which belong to infinitely many ans. Let me make a quick note of that. All right, so a limb soup an is precisely the set of all omega and omega which belong to infinitely many an. All right, so now here are the Borel-Cantelli lemmas. So let omega fp be a probability space, and suppose an n going from 1 to infinity subset of f is a sequence of events. Now what you do is you look at the summation n going from 1 to infinity p of an. Now there are only two possibilities, either sum n going from 1 to infinity p of an is finite, or sum n going from 1 to infinity p of an is infinity. So the first half of Borel-Cantelli says if sum n going from 1 to infinity p of an is finite, then p of limb soup of an must be 0. Now the second half almost says that if the sum n going from 1 to infinity of p of an is infinity, then p of limb soup is 1. And the reason I say almost is because you need one extra assumption. So the second part says that suppose the events a1, a2, and so on are independent. So this extra assumption is needed in part 2. And sum n going from 1 to infinity p of an is infinity, and p of limb soup an is 1. In the first part, whether or not the ans are independent is irrelevant. We saw the proof of 1 last time. We went through this. Then we were going through the proof of part 2. So we said suppose a1, a2, and so on are independent, and sum n going from 1 to infinity p of an is infinity. What do we want to do? We want to show that p of intersection n going from 1 to infinity union k going from n to infinity ak is 1. Okay, now you know that if you want to show the probability of a set is 1, it is enough to show that the probability of its complement is 0. So last time we went over De Morgan's laws and all that fun stuff, and what we concluded was it suffices to show that p of union n going from 1 to infinity intersection k going from n to infinity ak complement is 0. And that's what we were in the middle of doing. So here's what we'll do. Let n be a natural number, and suppose m is greater than or equal to n. So consider the probability. Okay, by the way, remember, note that in this expression, you have AK complement, okay? So note that here, inside you have intersection, outside you have union, and here you have the AK complements, okay? So what you do is consider the probability intersection K going from N to M AK complement. All right, so now what can you say? You can say that by independence, you have probability of the intersection is the product of the probabilities. So probability of the intersection K going from N to M AK complement is product K going from N to M P of AK complement. This is just the definition of independence. Okay, then you say that probability of AK complement must be 1 minus probability of AK. So you get product K going from N to M 1 minus p of ak. Then I'm using this fact. We will first finish the proof of Borel-Cantelli, then we will prove this fact. Right now, I will just ask you to believe me when I say that if x is greater than or equal to 0, then 1 minus x is less than or equal to e to the minus x. If you already know this, good for you. If not, you will know why it's true in about 5 minutes. But right now, let's just accept this. For x greater than or equal to 0, 1 minus x less than or equal to e to the negative x. Anyway, so now what you're going to have, if you use this thing, you'll have product k going from n to m, 1 minus p of ak is less than or equal to product k going from n to m, e to the minus p of ak. And so what should I do? So this is going to be what? This is just going to be equals e to the minus sum k going from n to m, p of ak. Right, this is just true by the laws of exponents. When I multiply e to something and I multiply a bunch of such things, I just get e to the sum. Okay. All right, so now what am I going to do? Let me just rewrite that main thing. P of intersection k going from n to m ak complement. This thing is less than or equal to e to the minus that. So less than or equal to e to the minus sum k going from n to m, p of ak complement. Right? All right, so now what I'm going to do is I'm going to say that p of the intersection k going from n to infinity, ak complement, this thing is the limit as m goes to infinity, p of intersection k going from n to m, ak complement. The reason this is true is because of a property of measures, actually a property of finite measures, which is continuity from above. Okay, so you can think of this as the sequence G sub m. Okay, and then you can say that Gm contains Gm plus 1, dot, 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 and the intersection of all of these G's is going to be this guy. Okay, and so you will say that when you are approximating a set from outside by a sequence of decreasing measurable sets, probability of the intersection is the limit of the probabilities as long as you have a finite measure. And in this case, you have a probability measure, so of course it is finite. All right, so you get this. But what is this? Now remember that you have this inequality available to you. So if I take the limit on the left side, that should be less than or equal to the limit on the right side. Now, just to be very careful, I don't know that the limit of the right side exists, but I certainly know that the lim sup will exist. Lim sup, m goes to infinity, e to the minus summation k going from n to m, p of ak. But wait a second, this is going to be 0. Why is this going to be 0? The reason it's going to be 0 is because remember that as m goes to infinity, this summation goes to infinity, right? By hypothesis, the sum of p of ak over all k was finite. Now, right, that was what the hypothesis was. Now, of course, at this point, you may object and you may say, wait, the sum here starts only from n. And I say it doesn't matter, right? Because if you have an infinite series and you start the series from first term plus second term plus third term plus dot, 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 that will converge if and only if 100th term plus 101st term plus 102nd term plus dot, dot, dot converges. Where you start the infinite series does not determine whether or not it converges. So this infinite series also diverges. So let me just make a quick note of that. And this is since a sum k sum k going from n to infinity, p of ak equals infinity for every k. Of course, this was not there in the assumption, but this is something you know, right? If I have an infinite series, then if I start the series a few terms late, then the convergence or divergence is going to be unaffected. All right, so now we're almost done. So now what can you say? Now you can say that this guy is a null set, right? And the thing you were interested in is a countable union of null sets. So thus, for any n, intersection k going from n to infinity, a k complement is a null set. But wait, a countable union of null sets is also null. So the union n going from 1 to infinity, the intersection k going from n to infinity, a k complement is also a null set. Right? This just follows from the fact that a countable union of null sets is null. All right, and now we're done, right? So what have we shown? I.e., we have shown that probability of union n going from 1 to infinity, intersection k going from n to infinity, a k complement is 0. And remember that that is equivalent to what we wanted to show, because somewhere earlier we said this thing, right? It suffices to show that this highlighted thingy is okay, never mind that, sorry. That is correct, that's not wrong, but it suffices to show this thing. And this is exactly what we have now shown. And so, yes, the second half of Borel-Cantelli has been proved. Any questions with this? Any questions? All right, so that takes care of the Borel-Cantelli lemma. Now, the one hole that we need to fill in, which had to do with this 1 minus x, e to the minus x and all that. So let's sneak in a note here. Okay, so let x be greater than or equal to 0. Now, e to the minus x minus 1 is e to the minus x minus e to the 0. And this ends up being the integral from 0 to x minus e to the minus s ds. And you will ask, why is this true? Well, this is true simply by the fundamental theorem of calculus. Fundamental theorem of calculus. Right? And now what are you going to have? Now you'll say e to the minus s is less than or equal to 1 for s greater than or equal to 0. Remember, here we're starting with x greater than or equal to 0. So this x is non-negative. So you're integrating from 0 to x. So the interval you're integrating over consists of non-negative numbers. For non-negative numbers, s e to the minus s is less than or equal to 1. Okay, so what does that involve? That means that minus e to the minus s is greater than or equal to minus 1. This implies that integral 0 to x minus e to the minus s ds is greater than or equal to minus integral 0 to x 1 ds. Right, so what is this, the right side? The right side is just going to be minus x. And what are you going to get on the left side? On the left side, you're going to get, okay, so that is what you want. So what have you shown? You have shown that e to the minus x minus 1 equals this guy. And this guy is greater than or equal to minus x. Therefore, e to the minus x minus 1 is greater than or equal to minus x. This implies e to the minus x minus 1 greater than or equal to minus x. And so what does this mean? This means that, what is the inequality? 1 minus x. This means that 1 minus x is less than or equal to e to the minus x. And that is exactly the fact that we used. So this verifies the property that we used in the course of the proof. Any questions so far? All right, so for the next thing I'm going to do, I need a little feedback from you. So I want to know, I'm going to type up something here in the chat box, and I want to know how many of you have seen this. How many of you have seen convergence in measure? Or have you seen convergence in measure?
I think this definition was introduced in major theory course.
I beg your pardon?
That definition was introduced by Ladawala sir in major theory course last time.
Okay, but did he spend much time talking about it?
I think no.
No. Okay, so do you know what convergence in measure is?
Yeah, definition, but right now I'm not. I forgot.
Right now you forgot it. Okay, this is helpful. This is exactly what I want to know, because I know that the measure theory course here does not always do convergence in measure. That's why I'm asking you whether you've done it, how much you remember it, and so on. Okay, so then we will spend some time talking about convergence in measure. Okay, now one more thing. Have you seen convergence almost everywhere? Yes, the answer is yes. You have seen it in this course also, okay? So yes, you have seen convergence almost everywhere. Convergence almost everywhere means that you can throw away a null set, and once you're done throwing away a null set, on whatever is left, you do have convergence. So yes, I'm answering for you. Yes, you have seen convergence in measure because we have done it. In probability, it's called convergence almost surely. All right, but no, I may have said the wrong thing. Sorry. Convergence almost everywhere we have done. In probability theory, it's called convergence almost surely. Yes, that is a true statement. Convergence in measure, it seems, was mentioned in the measure theory course, but probably not elaborated on. That is fine. But so let's get to convergence in measure. Now again, okay, so here's a spoiler alert. Convergence almost everywhere in analysis is convergence almost surely in probability. Convergence in measure also has another name in probability. It's called convergence in probability. Okay, so just like, by the way, you can see the iPad, I hope, right? Just like convergence almost everywhere had a different name in probability, but the idea was the same. Similarly, convergence in measure has a different name in probability, but the idea is exactly the same. So I can talk about convergence in measure and then say, okay, if I'm on a probability space, instead of saying convergence in measure, I will say convergence in probability. And instead of having measurable functions, I will have random variables. All right. So that is my goal now. My goal is to talk about, in the measure theory setting, what does convergence in measure mean? How is it related to convergence almost everywhere? That is the question I want to ask. Then, of course, as soon as I answer that question, I will have the answer to the question, how are convergence almost surely and convergence and probability related? Because at this point, you will remind yourself that a probability space is a special case of a measure space. All right. Okay. So now what I'm going to do is, before I introduce a definition of convergence in measure, I want to start with an example. So let me start with the following. Let me take omega to be 0, 1. Let me take the sigma algebra to be the Borel sigma algebra on 0, 1. And let me take mu to be Lebesgue measure on 0, 1. Now I'm going to use the language of analysis, but note that this is actually a probability space. Okay, so this is actually a probability space, so you could consider this as an example of probability also. Anyway, what I'm going to do is I'm going to start drawing some pictures. In the pictures, I will draw a sequence of functions. And then we'll ask some questions. Does the sequence of functions converge? Yes, no, etc., etc. All right, so let's get to it. Okay, sorry. Okay, let me use the color facility here. That will be actually helpful. So let me draw a horizontal line here. Oh, artwork is really bad. Very strange. All right. Sorry, guys. Somebody seems to keep calling. I don't know why. Okay. Oh, that was done freehand. Remarkably good for freehand. Okay. Okay. At some point, you will excuse me from this painful drawing exercise because you will see that my artwork is not very good, and it is giving little added value. So in order to save a little bit of time, I'm not going to draw all the pictures, okay? Of course, I couldn't possibly draw them because we're talking of infinitely many pictures. Oh, good Lord, drawing is not easy. I don't know how people do this. All right. Okay. Now let me see if I have not messed things up. Hopefully I've not messed things up. Now you're going to have to imagine a little bit because my drawing is not drawn to scale. Okay. So suspend your disbelief. This is the interval 0, 1, and this is the point 1/2. Again, this is my first function, f1. So what is the function f1? It is 1 between 0 and a half, and it is 0 after that. Here I've arbitrarily taken it to be right continuous, but it's not going to matter. In the second picture, I have f2. F2, on the other hand, is a 0 between 0 and a half, and then it is 1 between a half and 1. Okay. Then I have the function f3. Now f3 is 1 between 0 and 1/4, and then it is, no, f3 is 1 between 0 and a quarter, and after that it is 0. Now this picture is badly not drawn to scale. Here f4 is 0 between 0 and a quarter, then it's 1 between a quarter and a half, and after that it's 0. Are you guys getting the hang of this? Yes? No? Okay, so what did I do in the first two functions? I took the interval from 0 to a half, 0 to 1, and I broke it up into two pieces. The first function was 1 on the first half, 0 on the second. The second function was 0 on the first part, 1 on the second. Okay. Then I'm going to take the interval from 0 to 1 and break it up into 4 pieces. The first function is 1 on the first quarter, 0 everywhere else. The second function is 0 on the first quarter, 1 on the second quarter, 0 everywhere else. The third and fourth functions I have not drawn. f5 and f6 I have not drawn. And I will break up the interval from 0 to 1 into 0, 1 over 8, dot, 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 up to 1. So I will break up each interval from 0 to 1 into 8 pieces. And then I have a function which is 1 on the first piece, 0 everywhere else, then 1. Okay, this magnificent picture is this. Okay, so I have a function which is 1 on the first piece, 0 everywhere else. Right, 1 on the first piece, 0 everywhere else. This is 1 on the second piece, 0 everywhere else, and so on. I'm not drawing anymore. Is the pattern clear? Can somebody please give me some confirmation if the pattern is clear? So here I will have two functions like this. Here I will have 4 functions. Here I will have 8 functions. And I will keep doing this. The next time I'll have 16 functions and so on and so forth. Any questions with this? Any questions with the sequence of functions I've drawn? Okay, so here there are 2 functions. There are going to be 4 functions when you're breaking up 0, 1 into quarters. There are going to be 8 functions when you're breaking 0, 1 into 8s. There are going to be 16 functions when you're breaking 0, 1 into 16 pieces and so on. Now let me ask you a question. All right, so here is the question. Does fn converge at all as n goes to infinity? To word it in another way, is there any x in the open interval 0, 1 with the property that limit n goes to infinity, fn of x exists? What do you guys say? What do you think the answer to this question is? Anybody? Okay, it's a 2-letter word. I'll give you a hint. Hello, I'm teaching a class right now. All right, the answer is no. There is no value of x for which this converges. Why is this true? Okay, again, so what you'll do is you take any point you like. Okay, take any point here, call it P. As you go into the sequence, let me take this point x here. Okay? As you go into the sequence, you will invariably come across functions where f is 0 at x, and every now and then you will come across a function which is 1 at x. And this will happen no matter how far you go. I would be a little challenged to explain that a little better, so let me say that once again. Take any x in the open interval 0, 1. As you go ahead in the sequence, okay, you will have a situation where for many, many functions, f will be 0 at x. And then suddenly you'll have in one function, f will be 1 at x. And then again, the pattern will repeat, f will be 0 at x many times, and then suddenly it will be 1 at x. So the point is that no, the sequence does not converge anywhere. Because if I take any x, I can, and no matter how far into the sequence I go, I will find some function which is 0 at x and some function which is 1 at x. Any questions with this? No. Okay. Any questions? So again, if you have not fully understood the drawing, you can try and do a better job. Once again, the idea is, in the first 2 cases, I break the interval from 0 to 1 into 2 pieces. The first function is 1 on the first part, 0 on the second. The second function is 0 on the first part, 1 on the second. Then, so that takes care of f1, f2. Now for f3, f4, f5, f6. Here I break the interval from 0 to 1 into 4 pieces. f3 is 1 on the first quarter, 0 everywhere else. f4 is 1 on the second quarter, 0 everywhere else. Similarly for f5, f6. Then I'm going to have f7, f8, f9, and there are going to be 8 such things. So here I'll take the interval from 0 to 1, I'll break it up into 8 pieces. The first guy is going to be 1 on the first 8, the second guy is going to be 1 on the second 8, and so on and so forth. So if this wasn't clear to you, I invite you to go back home and draw this nicely and convince yourself that this is true. Okay, let me ask you another question. Is there any subsequence of Fn which converges? Oh, come on. What are your thoughts? Yes, there is a subsequence which converges. Here is how you can see it. Suppose I take an x here, right? Now, what I will do is, okay, so I want to basically come up with a subsequence of functions which converges to 0. All right, so what I'll do is I'll take f1, I'll take f3, I'll take this guy, and so on. In other words, every time I'm breaking that interval into some power of 2, I will only take the first function and none of the others. So I'll take f1, I'll leave f2. Then I'll take f3, I'll leave f4, f5, I'll leave f4, f5, f6. Then I'll take f7, and then I'll leave the remaining 7. And then I'll take the first f, then I'll leave the remaining 15, and so on. So as you can see, the graphs are going to be this, getting smaller, getting still smaller, and so on. So that subsequence is going to converge to 0 for every x and 0, 1. I will leave it to you to write that out because I think it will be a little difficult for me to do that. In any case, if you haven't fully understood it, you will have the video recording of this lecture, a good supply of pen, paper, and coffee. So I'll leave it to you to figure out. But the point is, if I take f1, f3, this is going to be f7, and then so I take the first function of every power of 2 series and leave out the rest. You will get a sequence of functions that converges to 0 everywhere. But if you think of this as let me just, we were supposed to bring in analogies, right? Let's say that these are, okay, let's say you think in terms of area. If I look at the area under these functions, is the area under the functions going to 0? Please somebody answer that. Yes, it is going to 0. The thing is, if you look at the set of points where the function is non-zero, that is getting smaller and smaller. Here, the function is non-zero on a set. Here, the function is non-zero on a set of measure a half. Here, the function is non-zero on a set of measure 1/4. Here, the function is non-zero on a set of measure 1/8. In the next series, the function will be non-zero on a set of measure 1/16. So yes, the function is not converging anywhere, but if you look at the set of points where the function is big, so to speak, that set keeps getting smaller and smaller as you go further out into the sequence. All right, anyway, this sequence of functions Fn converges in measure. Okay, before I go any further, let me just mention that F4, F5, F3, F4, F5, F6. I have not drawn these. Then this guy is F7, this is F8, and then there are going to be a few more in this series and so on. Okay, so Fn converges to F in measure. Now at this point, you're probably scratching your head and saying, I don't know what convergence in measure is. And I say, well, we will sort that out on the next slide. But this was just to give you an idea. What is one property of the sequence of functions? If I look at the set of points, okay, so let me rephrase that. I have not said this well. Fn converges to 0 in measure. Okay, so let's take this sentence, which I'm now highlighting, and describe it in words. Okay, so Fn converges to 0 in measure means take any epsilon. Okay, now look at the set of points where the difference between Fn and 0 is more than epsilon. And now look at the measure of that set. Don't look at where the set is, just look at the measure of that set. If the measure of that set keeps getting smaller and smaller, that means that Fn converges to 0 in measure. So once again, when I say Fn converges to 0 in measure, what I'm saying is the following. Take any epsilon. Look at the set of points where the difference between Fn and 0 is more than epsilon. Look at the measure of that set. If the measure of that set goes to 0 as n goes to infinity, then you say that Fn converges to 0 in measure. All right, the point is the set is allowed to move around, as you can clearly see here. Right here, you can see that the set where the function is non-zero moves around a lot. Here it's here, then it's there, then it moves around, and so on. Anyway, hopefully this is enough preamble to state what we mean by convergence in measure. We will state it even when instead of 0 you have some other function here. But anyway, this whole thing was written down simply to motivate what convergence in measure is, and so that you have a concrete example in mind when somebody stops you in the cafeteria and asks you what is convergence in measure. Okay, so here is what, let's write this down. So this is about types of convergence. Once again, for the umpteenth time, we're stating it in terms of analysis, but of course, probability space is a measure space with total measure 1, random variables are measurable functions. So of course, whatever we're saying here will carry over to probability. The names may change and they will change. Okay. So here's what's going on. So let omega f p, oh no, I don't want omega f p, I want omega f mu. So let omega f mu be a measure space. Then let Fn, f be measurable functions from omega to r. Okay, so now we're going to make 3 definitions here. So here's the first one. Say that Fn converges to f almost everywhere. If you want to emphasize the measure, you might say mu almost everywhere. And you know the answer to this. What this means is if you can throw away a null set such that on whatever is remaining, Fn converges to f pointwise. So if there exists a set n in f with mu n equals 0, such that for all omega, in omega take away n, we have Fn omega converges to f of omega as n goes to infinity. Okay. All right, so this is a familiar definition. There's nothing new here. So here is the second one. Say that Fn converges to f in measure if for every epsilon greater than 0, if I look at the set of all x in omega such that absolute value of Fn of x minus f of x is greater than epsilon, if I look at this set, and now I look at the measure of this set, then this thing goes to 0 as n goes to infinity. Right, so this is exactly what we said. Look at the set of all points where the difference between Fn and f is more than epsilon. Look at the measure of that set. The measure of that set should go to 0 if you are to have convergence in measure. The third thing is what you mean by convergence in LP. So if integral absolute value f to the n p less than infinity, of course here I'm integrating with respect to the measure mu. Integral absolute value of f to the p is less than infinity. Okay, so here 1 less than or equal to p less than infinity. We say that Fn converges to F in LP if integral absolute value of Fn minus F to the P goes to 0 as n goes to infinity. All right, so here we have talked about 3 different modes of convergence for a sequence of measurable functions. Convergence almost everywhere, convergence in measure, and convergence in LP. Any questions with what's being said here? All right, so these are 3 different senses in which a sequence of functions can converge. Actually, I'm not saying these are the only 3 senses in which a sequence of functions can converge, but I'm saying these are 3 important senses in which a sequence of functions can converge, and senses in which we will be quite interested. Any questions? All right, so here is what is the relation between them. Suppose Fn converges to F almost everywhere. If mu of omega is finite, then Fn converges to F in measure. Okay. I will write this down, so no need to try and run and take notes. Then, if Fn converges to F in measure, then there is a subsequence which converges to F almost everywhere. Finally, if Fn converges to F in LP, then Fn converges to F in measure. Of course, these 3 statements I've made are not the last word in how these things are related. You may say, stop. What is the relation between almost everywhere and an LP? When does almost everywhere imply LP, vice versa, etc., etc.? And I will say we are not going to get into that. So we're just making some limited statements about how these types of convergence are related. All right. So where should I go? So let's now explore. The relation between these types of convergence. All right, so the next proposition, I'm going to write down exactly what I said. So here's the proposition. By the way, I'm now going to repeat the notation. Okay, so omega f mu is a measure space. Fn, f are measurable functions taking omega to r. Okay? So that stays the same. So our first claim. So suppose mu of omega is less than infinity. If Fn converges to f mu almost everywhere, then Fn converges to f in measure. And this is what we just stated a couple of minutes back. Then, if Fn converges to f in measure, then there is a subsequence f and j such that f and j converges to f mu almost everywhere. And 3, so suppose integral abs fn to the p d mu is finite. Integral absolute value of f to the p d mu is finite for some 1 less than or equal to p less than infinity. if Fn converges to F in LP, then Fn converges to F in measure. All right, any questions with this? Okay, so I've just basically repeated what I said. So now let's prove these one by one. So proof. So let's start with one. So suppose mu of omega is less than infinity. Okay? And that Fn converges to F mu almost everywhere. Okay. So now we want to show that Fn converges to F in measures. So let epsilon greater than 0 be given. Right? So what do we want to show? We want to show that mu of omega in omega such that absolute value of Fn of omega minus F of omega greater than epsilon goes to 0 as n goes to infinity. Right? This is exactly what the definition of convergence in measure would have us do. Okay, so let's prove this. So let An be the set of all omega in omega such that absolute value of Fn omega minus F omega is greater than epsilon. Okay, by the way, note that here I used x, and on the next page I used omega. It's not a big deal. When you're doing your work, just be consistent, stick to one of them. Doesn't matter which one it is. If it's probability, it's customary to use omega. But okay, since this was in measures, out of force, so happy I wrote x. If it bothers you, I can change it. Does it bother you? Anyone? Anyone? Okay, it bothers me, so let me change it. Fn. All right, it bothers me, so I've changed it. All right. So let An be this. Right? We want to show that the measure of An goes to 0. Okay. So let's do the following. Let B be the set of all omega in omega such that Fn omega converges to F omega. Okay, what do we know? We know that the complement of B has 0 measure, right? Because B is the set where Fn converges to F. We know that happens almost everywhere, which means that measure of B complement is 0. So we know that mu of omega minus B is 0. Okay, so now what can you say? So if omega is in B, okay, so if omega is in B, that means F as n gets large, Fn gets arbitrarily close to F, which means that for n big enough, this thing will fail. Let me repeat that. Suppose omega is in B. That means Fn omega converges to F omega, which means as n goes to infinity, Fn omega gets closer and closer and closer to F omega, which means that for n big enough, the distance between Fn omega and F omega becomes arbitrarily small, which means for n big enough, this condition will fail. In other words, omega will not be in An for n large enough. Okay, so let's write that down. If omega is in B, then absolute value of Fn omega minus F of omega can be made arbitrarily small by making n large enough, right? So this is less than or equal to epsilon for n large enough. So what do you say? I.e. omega is not in an for n large enough. In other words, indicator an of omega is 0 for n large enough. Right, because if omega is not in an for n large enough, that means indicator an evaluated at omega is 0 for n large enough. So what does this mean? This means that I.e. indicator an of omega goes to 0 as n goes to infinity. Right. All right, so now what do we have? Thus, for omega in B, indicator an of omega goes to 0. So what does that mean? Remember, the complement of B has 0 measure, which means thus indicator an of omega, and let me not write omega, indicator an goes to 0, mu almost everywhere. Okay, and now I'll use dominated convergence theorem. Actually, I'll use bounded convergence theorem. So what does bounded convergence theorem say? It says suppose I have a sequence of measurable functions converging to some limit. And let's say that everything is bounded. Okay? Then the limit of the integrals is the integral of the limits. So bounded convergence theorem, of course, is a special case of dominated convergence theorem. So here's what we'll say. So now indicator an is less than or equal to the number 1. Here is where you use finiteness of mu. Since mu is finite, right, the function 1 is integrable. Okay, so if mu were not finite, the function 1 would not be integrable. And so now 1 is your dominating function, and so you'll get by Lebesgue dominated convergence theorem, you'll have mu of an, which is the integral over omega indicator an d mu goes to 0, and that is exactly what we wanted to show. I'm sorry we have gone 1 minute over, so I want to stop right there. Any questions? I'm also going to stop